introduction.
Okay.
Yeah. Okay. Hello, everyone. And I will start a brief introduction about our ISL as student lecture series talk platform. Our ISL talk provides a platform to share your recent research work connected by graduate students and learn research ideas from the peers. And this our sector presentation topics are made from the different SCSE labs, and our presenter is carefully selected as well. These events are aimed for the graduate students of NTU, but all are welcome. And also for students with the GAP hours requirement, this event can be counted as the 2 GAP hours for presenter as a bonus. So next, I need to introduce our today's presenter, Pascal. And he is a PhD student in computer science at Nanyang Technological University. And Pascal is a second year PhD, and his main research interest is geospatial information system and the application to logistics and smart cities. His research is currently exploring applications of deep learning to enhance geospatial databases through entity link and automatic knowledge graphs construction. Today's topic is geospatial interlink. This talk introduces geospatial entity resolution, an algorithm that leverages the power of pre-trained language models and graph attention neural networks in order to make automatic geospatial data integration possible. Okay, so I will pass the microphone to Pascal. And are you ready?
Yes. Hi, Gawai. Okay, thanks for introducing me, and thanks for hosting me. Today talk is titled Geospatial Interlinking, and is from my first publication, which is a joint work between NTU and Alibaba, and is titled Geospatial Entity Resolution, and is accepted in WWW 2022. So as you may understand already, today we are talking about geospatial data that is nowadays the core of many web applications. So you can think of Foursquare, which is a location-based social network, or Yelp, which is a social network based on reviews of businesses, and OSM, which is a global map, which is annotated by volunteers. So many applications rely on voluntarily annotated maps like OSM, but even more traditional social networks like Instagram or Facebook heavily rely on a geospatial database for their application. An important challenge of geospatial entity resolution and for service providers is to first of all, when they decide to leverage geospatial data for their application, the main challenge that arises is that each source of geospatial data has only a partial coverage of the whole picture. So to merge data in a comprehensive database, the duplication is needed. So the duplication is achieved through entity resolution, which is the second part of the title of this paper. So entity resolution, traditional entity resolution, refers to a model that is able to infer if two records in two different databases refer to the same entity in the real world. In this case, we are working with geospatial data. We want to predict if two POIs, which stands for point of interest, in two different geospatial databases refer to the same POI in the real world. So as you can see in this simple example, we have two Starbucks, the red one from one source and the blue one from another. And we want to understand if these two entities are actually the same POI, the same Starbucks in the real world, or they are two different places. They can be the same even though the position is not exactly the same, because geopositioning systems are not very accurate. So to define the problem of geospatial entity resolution or geospatial interlinking, we can see this simple picture with three examples. As you can see in the first one, that also have a good representation of the challenges of this work. So as you can see in this in the first example, wine and spirits and fine wine and good spirits actually refer to the same place in the real world in this case, but their names are not exactly the same. So we cannot expect the name or the address or any feature of the two records to exactly coincide. In the second example, we can see that we cannot rely on simple string similarity measures. In fact, Mitchell's dinner and Michelle's dinner are very similar strings, but a small difference, in this case in the name, Mitchell and Michelle, is a strong signal that these two records may not be the same. So each word should play a different role in this task. So we need a model that is able to assign each word a different importance. The last example is again two Starbucks, which are very close in space and have, of course, the same name, but they are not the same. And this could seem unreasonable, that two PIs with the same name and very close in space are not exactly the same in the real world. And this can be inferred only looking, first of all, at the district, so at the neighborhood. These two PIs are located in Orchard Road, which is a quite busy district in Singapore. And also Starbucks, as we all know, is a popular chain of PIs. So it's reasonable to have two Starbucks at a very in a close distance in Orchard district. So to summarize the challenges, first of all, we need to use language modeling techniques in contrast with simple string similarity measures. We need to use a distance information and integrate it in the learning framework, in contrast to previous methods that still use human designed thresholds. And we also want to leverage contextual information from the neighborhood to learn interesting information about the neighborhood and the POI itself, which is a major contribution in this work. So to give a quick pass to the related work, as you can see from these two pictures, pre-trained language models heavily dominate entity matching and entity resolution. I mean, traditional entity resolution. Ditto is a pioneering work in the use of pre-trained language models like Bert or Roberta in entity matching, and they present. They just simply use a pre-trained language model and present some very effective data augmentation techniques. The second model is joint BERT, which just shows that forcing the model to also predict the ID of the product can improve the performance of the model. This is not really suitable for our case, but is an interesting result. Geospatial, the related work in geospatial entity matching, the main solution still heavily rely on word similarity measures for the textual part. And for the geographical part, they rely on human designed rules that are expensive and require human knowledge and expert knowledge. Also, as I showed you in the previous examples, string similarity measures are not enough since they they produce a very static result that cannot assign different importance to different words in different contexts. So to solve these challenges, we propose GeoER, which is composed of two phases. The first one is the blocking phase, and the second is the matching phase. So the blocking phase is very popular in every entity resolution algorithm. Basically, it tries to make the whole algorithm faster, because if we want to compare each record in one database with every other record in the other database, the result will be too expensive, computationally expensive, and would require a complete Cartesian product. Like in this example, we have two databases of 3 records each. The full Cartesian product will require 9 comparisons. Instead, using a simple blocking rule, we retrieve likely candidates much faster without using heavy deep learning models. And in our case, in this example, we retrieve only 3 candidates, which are highlighted by the arrows. Yeah, we design a fast and effective blocking rule for geospatial ER, which depends on the spatial distance and name similarity. So for each POI in the first database, we select all the POIs in the second database that are physically close, lower than a specified distance threshold, and have a name similarity that is higher than a threshold. We use a Levenshtein distance. So we use a quite high geospatial distance threshold because we don't want to lose true positive samples in this phase. So this is due to the fact that some POIs are quite big, like airports or universities. So the positions for these 2 POIs in the 2 databases may have been recorded in very distant places. So to maximize the recall, we use a high distance threshold and a quite small Levenshtein threshold, which is very easy to satisfy. So as you may understand, we don't even need to design a negative sampling schema, because each neighbor that we find in the blocking rule, in the blocking phase, for each candidate couple, we check in the ground truth if they are actually if they match or not, so if they refer to the same real world entity or not, and we label them accordingly. So we have a data set that is made of very informative and hard to classify examples. In this case, so every candidate couple in the dataset will be physically close, and will have some sort of name similarity, some string similarity in the name. So the second part is the matching model, which is the main contribution in every entity resolution papers, in most of them. Our matching model consists of 3 main components, which are a transformer-based language model, a distance embedding component, and a neighborhood attention component. So the first one is the language model for textual attributes matching. We use BERT, pre-trained language model, because to compare the textual parts, because it's the language model that best performed in our experiments. So as you can see, we first serialize the input for the language model. The first token is the CLS token, which is a special token for classification purposes. Then T1 represents the entire set of words that represent the first entity. Then a separator token, the words referring to the second entity, and a separator token. So as you can see in the picture, we only extract the CLS token, which is a quite common approach when using a language model for classification. The second component is the distance embedding component. Is quite simple, but also very effective, because we compute the distance between the POIs we are comparing using Haversine formula. We scale it to be between -1 and 1, and we embed it in a fixed size array through a multiplication for a vector of learnable parameters. The output of this component is concatenated to the output of the other components. So the last component, which is quite novel and a main contribution to improve the performance of our solution, is the neighborhood attention component, which, as I introduced before, gives important information about the district and the POI itself. So we decide to use graph attention networks in contrast to graph convolutional networks, because we believe that not every neighbor is equally important, and the algorithm should learn to pay different attention to each neighbor, depending on the semantic and the geospatial similarity. So to achieve this, we compute an embedding for the two entities and all their neighbors, and we apply a linear transformation whose result is called ZI. As you can see, we concatenate ZI with which is the embedding for the main entity, both the two entities. So we repeat this procedure for both the entities, and we concatenate the embedding of the main entity with each neighbor, which is ZJ, one at a time. And we compute a normalized attention, which is parameterized by the vector of learnable parameters A. So EIJ is the normalized attention score, and then we apply softmax across all the neighbors. In this way, all the attention scores are numbers between 0 and 1, and they all will sum to 1. So we compute finally a context embedding for the neighborhood, summing each the embedding of each neighbors multiplied, weighted by their attention score, which is alpha ij. So alpha ij exactly represent how much attention the first entity EI should pay to each neighbor EJ. And then we apply another activation function, in this case the ReLU. We improve this approach of just using graph attention networks, introducing an attention bias to encourage the model to pay more attention to closer neighbors, because in the first in this part the model can learn to pay attention to semantically similar neighbors, which is very important, but cannot perceive the distance between the central entity and each neighbor. So to make this possible, we add an attention bias, which simply depends on phi, which is a learnable parameter, and 1 over dij, where that is the distance between entity I and entity j. In this way, we push the model to pay more attention to closer neighbors, and in contrast, to pay less attention to neighbors that are more further away. The model will learn through phi how much how important the distance part should be. So the three components outputs are concatenated in a linear layer, and we and we apply we are concatenated and we apply a linear layer to obtain the final prediction. The model is optimized using cross entropy loss for binary classification. So the loss function is a binary loss function because we want to predict only match or no match. And we use Adam optimizer with a linearly decreasing learning rate schedule and a batch size of 32. we evaluate our algorithm on 8 real-world datasets from 4 cities and 3 different sources. We join OSM, OpenStreetMap, and Foursquare in Singapore, Edinburgh, Toronto, and Pittsburgh, and the OSM and Yelp in the same cities. So the second column shows the size of the dataset, including training, validation, and test. And the last column shows then the amount of positive samples in percentage in each dataset. So we compare our algorithm to state-of-the-art solutions for ER and geospatial ER. So DeepMatcher is a pioneering work in the use of deep learning for traditional entity resolution. It actually leverages LSTMs with attention. Ditto uses pre-trained language models, as I introduced before, and SkyX is the state-of-the-art solution for geospatial ER. As you can see, the improvement of GeoER is significant and ranges from a minimum of 2.7% in the dataset of Edinburgh OSM Yelp, up to 7.2% in the dataset of Singapore OSM Foursquare. We perform an ablation study to evaluate the role that each component of GeoER has in the performance improvement. As expected, the distance embedding, even being the simplest part, plays a more important role and gives a higher improvement in terms of performance, which is 3.3% on average improvement across the 8 datasets. But also the neighborhood embedding, as you can see, gives a quite significant embedding of 1.7% on F1 score on average across all the datasets. That's it for my presentation. Thanks for the attention. Do you have any questions?
Yeah, thanks for Pascal. And so for our audience, if you have any questions, you can send questions in the chat box, or you can raise your hand or just unmute yourself and direct ask questions. So I will ask the first question. And notice that in this system, they have 3 components, and I'm curious about the inference time cost of this model. It can be applied in real time.
Sorry.
You can, yeah, and I'm curious about the inference time cost of this model.
Yeah. The cost of the model is comparable. I don't have a table here, but is comparable to Ditto and other algorithms that leverage pre-trained language models, which are basically the heaviest part, the heaviest component in this kind of models.
Yes.
So the most the most time expensive. Yes. Usually on entity resolution, the time cost is not a big deal because it's usually an improvement to databases. For example, if you want to join or integrate through databases, it's you perform the duplication only once. The only real concern is the computational complexity. If you have to compare each entity of one database to each entity of the other database using a heavy deep learning framework. For big databases, this becomes impossible. That's why we need blocking rules.
Okay, great. And I have another question. Is you adopted the BERT model is pre-trained model, or just
yes?
It's pre-trained, and also you will fine tune this BERT on your data set, right?
Yes. BERT is fine tuned. Yes, exactly. Yeah.
Okay, great. And have you tried not fine tune, just directly use it? And
yes, there are. there are many experiments on this, but the performance are almost always lower than using the pre-trained BERT. Yeah, this is the main reason of using a pre-trained language model. Yeah.
Yeah. Okay. Can you discuss some potential future work of this direction?
Potential future work could be to generalize this. Let me search for a suitable slide. Generalize this approach of, for example, entity resolution, not just limited to learn if two POIs are the same or not, but to be able to infer more relationships between POIs that could be geospatial relationships as well. So as we know, knowledge graphs are becoming increasingly important nowadays. But in the geospatial fields, most of the database are quite flat, like in this example, and there are not many relations between the entities. Geospatial knowledge graphs have a very high level relationships, like if a POI is inside a city is inside a country, and a country is neighboring another country. So these are very simple relationships and cannot be effectively leveraged when using these databases, for example, for recommendation, because they are very high level. So I think a very interesting direction will be to explore similar algorithms, but to not to limit them to just predict if two POIs are the same or not, but to predict fine-grained relationships between POIs, like competitiveness relationships or closeness relationships, so geospatial or semantic relationships.
Oh, okay, so great. And I have a follow-up question about the BERT model. And I noticed that recently, the many language model expect to achieve the zero shot or few shot abilities across various tasks. And is it possible to train a similar geospatial model to achieve the very powerful transferabilities?
This has two limitations, because first of all, in geospatial data, the meaning of the words is less important than for common language models, because a model is not really required to be able to understand, for example, English language. But because most of the words, as you can see in this example, are proper names of POIs or proper names of address numbers, so the meaning of the words sometimes is less important than the interaction between these words. So in general, when using, at least in my experience, when using a pre-trained language model, the convergence of the model in terms of number of steps or number of epochs is much faster than any other approach, like, for example, graph neural networks. So when you fine-tune a language model like BERT, in many times, not just in geospatial entity resolution, but also in traditional entity resolution, in one or two epochs, this model is able to reach the state of the art, the best performance it can achieve. So this is not really the case of few shot learning, but it can converge quite fast. When you use a model for a different task, a few shot is never really simple, because there is a BERT was trained on language modeling tasks, like masked language modeling or next sentence prediction. So you cannot expect the BERT to have some entity resolution capabilities without at least fine-tuning it.
Okay, great. And is this paper is the first paper?
Yes, this is my first paper.
And can you share some experience in your first paper submission and some difficulties or some?
Oh, yeah, yes. Well, I was lucky because this was accepted in the first case. But yeah, I think that it's always quite hard for a paper to be accepted because the reviewers are always, especially in top conferences, are very harsh on the evaluation of the paper. One weakness of this paper was in the experiment part because we didn't use enough comparison algorithm for our experiments, but it's not really easy to find suitable algorithms for this task. And yeah, I think also the writing and the presentation of the paper is very important. Even if you present a model that is made of many components, the paper should be easy and smooth to read, and should be clear what you are doing. This is always very appreciated. And yes, the number of dataset and number of comparison algorithms should be as high as possible. At least I learned this in my experience, and yes, many experiments should be carried to prove that the model is working and is not a matter of luck, as we know that in deep learning computing. Performing many different runs can always give some performance that is a bit higher, but it doesn't mean that it's due to the model design. In this case, we carried the main experiments on the performance, the ablation study, but also an experiment that I didn't report in these slides that shows that our model is able to have some quite good performances generalizing across cities. So if you train a GeoER on one city and you test on another city or even another source, like you train on Singapore OSM Foursquare and you test on Toronto OSM Yelp, the decrease in terms of performance is very marginal, and it's able to almost achieve the same performance. This is important because for a real world use case, you cannot have a training set for every city you are going to use the model. So it's very important to have a model that is able to generalize at least across cities.
Yeah, great. And I think from my personal experience, the most difficult part for first submission is no baselines. You have to set up your own baselines from scratch. Yes. Yeah. So this training is very long and boring, and also error point. And yeah, congratulations, you succeed. And for the audience, for the audience, if you have any questions about this paper or about the publications, you can raise your hand or just unmute yourself and direct ask. Okay, so we can wait for 1 minute. If we have no more questions, we will end this talk.
Sure.
Okay, so for the audience, if you have interest in ISAF's talk, or you have you recently have some publications, you can send your email to us, or just via other platforms like Facebook or Instagram, and express your interest in our ISAF talk platform, and we can invite you and present your work and broadcast it. Okay, seems no more questions. I will end this talk, and thank you, Pascal. And
thank you very much.
Yeah, thank you. Bye.
Thank you. Go away. Bye.